Okay, 3-6, analyzing lines of fit. So I'm going to show you today how to use a calculator to find the line of best fit. So basically, in the past, you were picking points to draw the line of fit or the trend line, but the calculator has a way of using linear regression, which is the method that is used to calculate the best line, the line that most fits the data accurately. So you're going to get it looking like this, y equals mx plus b. Now to do that, we're going to use Desmos. So Desmos, I have to thank Mr. Nunez for giving me the link to it, has a way of doing that. And the way you do it is by completing the table, and the table will be graphed here at the same time. And also, it'll give you the line of fit down here, or the line of best fit. So that's what we're going to be doing, okay? So let's look at example number one. This is example number one. Use linear regression to find the function, or to find the equation of the line of best fit for the data below. So guys, what we have to do is we have to take these numbers. So I'm going to make all the x's. Oh, I guess I have to split up the screen. Sorry, give me a second. Okay, so I have to split the numbers. So 1, 2, 4, 5, 7, 8, and 9. So you just hit enter and it'll make a new space for you. And then here you put your y's, so 5.4, 6.1, 8.1, and you can see it as every time I add another point, the line shifts a little bit because you have more data that it's taking into consideration. All right, so there's my table, and you can look at the graph. Right here you can see your scatter plot. These are the points, 1, 2, 3, 4, 5, 6, 7. Yep, those are the 7 points, and this is the line of best fit. Okay, so there's your graph. Now, your line of best fit is over here on this side, down here. Now, it gives you the format that it's giving it, it gives you the format slope-intercept. And right here is your slope and your intercept. So for example number one, your answer in this format, you would have to round it because you can't use all those numbers. So the slope is going to be 0.78. I would use 2 decimal places for this. You don't have to use more than 2. That's fine. X, and the B is right here. So I'm going to say here plus 4.69, and there's my line of best fit. And that's really all you have to do, guys. So in a regular calculator, you would have to go to statistics. That's what this kind of math is. You would make your table in statistics, and then you would plot the line of regression, and it would give you the line of regression, and you would get your equation, okay? So there you go. That's example number one. Let's go on to example number two, shall we? So for example number two, the correlation coefficient. So you need to copy this down, R. If you notice back in the graph, there was an R that was given. The R has a number value, and the number is going to be between -1 and 1. So it's going to usually be a decimal between -1 and 1. And what it tells you how strong the relationship is, how strong the correlation is. So if you get a number that's close to +1, it has a strong positive correlation. If you get a number that's closer to -1, you have a strong negative correlation. But also, you can have weak positive correlation if it's between like 0 and 0.5. That would be weak positive correlation. And you can also have weak negative correlation if it's between 0 and 0.5. So you're generally trying to tell me how strong the correlation is by looking at the R value. So for example, in the graph that we had here, the R is right here, 0.99. So if you look at that number, 0.99 would be very strong correlation. And what that means is, if you look at the points, they are very close to the line. They are very close to the line. there's a strong relationship between the line and the data points, okay? And that's what that means. Another example is if I give you, let's say, something like this. If you have an R that's a 0.1, I would say that would fit right here. That would be weak positive correlation. The line is going up, but the points are kind of scattered. If you get something like this, negative 0.6, that would be over here. And I would say that's moderate to strong negative correlation, but I would side on strong over weak. And yeah, that's example number 2. All right, so let's move on to example number 3. All right, example number 3, residuals. So I'm sorry I ran out of space here. Basically, a residual is when you take a y value minus the predicted y value. So if you write this, R is the actual amount minus the predicted amount. Now this can be confusing the first time you see it. Let me go back to the graph. Residuals, if I zoom in on this graph, residuals are if I take the point and measure how far away that point is from the line. So this one would have a negative residual, a negative residual. This would have a positive residual. This would have a negative residual, positive residual. Oh, that one's probably on the line. Actually, nope. If you zoom in, it has a small negative residual. So when you do that, you can tell what kind of residual each point has. And there's a residual for each point, okay? And the way they calculate it is by taking the point, the actual number, which is the point 5.4, and you subtract what the line says should happen. So if the line says it would be right here, at this point, you would take that and compare it to this. And that's what residuals do, okay? So let me put this away. Let's go to this example over here. So let's say here, right? If I want to calculate the residuals here, I have all the points. What I need though is this right here. I need this to give me the predicted amount because the line is the prediction. The line of best fit is the predicted values of what should be happening. All right, so what you can do for this is you can graph this. So we can take the graph again, but we have to change the coordinates. So let's change that real quick. Let me move this picture over so I can see the coordinates. All right, let me zoom out. So you can just delete and clear these out like one by one, delete, 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 delete. And you can use it again with different points. Now actually this one starts with 0. 1, 2, 3, 4, 5, 6. Oh, I moved it too far. You see, I was hitting enter. And enter adds another space. Okay, now I put these points. 832, 872, 905. Sorry, I know this is really interesting. 928, 903, 887, 863, and 867. Okay, so there are my points, right? Now if you notice, it's not here because I'm only focusing on 0 to 25. For this, I would have to zoom really high up. And you can zoom out by like using these buttons right here. And you notice they're kind of really squished together. So it's kind of hard to really look at this. In these situations, what I recommend you do is go to the graph settings right here. And we're going to change the domain and the range, okay? So basically, if I'm using my x values, I only need from 0 to 7. So I'm going to put from 0 to 7 for my domain and range. Actually, I want to delete this whole thing. 0 to 7 for the x values. I don't need more than that. You can go to 10 just to keep it simple also. We'll give it a little bit of space. And then for the y values, I'm dealing with 800, 900, right? So what you can do is you can focus on the 800s, but I'm going to go, let's say 0 to, not 900 because there's points bigger than 900, 1,000. And there it is. And it's a little bit more clear here. You can see kind of the graph here that kind of looks right. And this kind of looks like what they gave you in the picture, right? So you have that information. Now, what normally I would tell you to do is now find the values of the points. So right there, that's the point here. So what you would have to do, I can close this now because I have this. When I'm comparing the first point at 0, the actual number is, sorry, let me move this over here so you can see what I'm saying. The actual number is what is on the table. And the table has 832. What the line says I should have gotten is 877. And I subtract that, it'll give me a residual. And I can do it for all the points. Right here, if I can, I wonder if I can change the point. Oh, it's kind of the only one. I think I'd have to zoom in to find out what the point is. Say if I zoom in right here. So at 1, it says it's 878 on the line. So the actual point for the next point would be 872. But it says there it should be 878. And right now, because of time, I'm not including decimals. I'm just kind of doing whole numbers. Right here, for this point at, this is 3. No, 2. This is 905. But it says it should be 879. 879. So we have 905 minus 879. And you would do that for all the points. You would compare the actual point minus what the line predicts would happen. Okay? So then we would subtract. We would subtract it and we would get the residuals for these points. So let me just do that real quickly. So for example, these two, this would be like negative 45. This one would be negative 6. This one, this one would be, let's see, that's 21, 26. And you would do it for all your points to calculate the residuals. Now, I'm going to give you a little shortcut here. Right here, there's a button on the graphing for the plots, residuals. It'll give you the residual if you hit this. And guys, look at the numbers right there. Look at what it is. Negative 45, negative 6, 26. And if you keep doing it for every point, you would calculate these residuals. Okay? And yeah, that is a quick way to do residuals using the graphing calculator. Now I should also show you this before we move on. If I go down here back to 0, this is called a residual plot. Let me zoom out a little bit. This is a graph of those residuals. So imagine if I ignored the y's and I just focus on the residuals. What was the residual at 0? Negative 45. What was the residual at 1? Negative 6. What is the residual at 2? 25. 3, 46. So this is called a residual plot, and it just tells you how far away the points were from the line. Okay, so that's a residual plot. And that's really it for number 3. I don't believe we have to do anything else for that. I think we're good. Let me just make sure I'm missing. Okay, so let's go to example number 4. So before we do this question, you need to copy this down. Let me put this back over here. Interpolation and extrapolation. So interpolation is when you're estimating within the data. Extrapolation is when you're predicting data outside the given values. So for example, let's say there was no point right here. Let's just say this is 5, right? There's no point here at 5. So what would be the point? What do you think the point would be? If we were to add a point to the data, where would that point be? Well, we would think that it's right here. It would be close to the line. This would be an example of interpolation. You're estimating within the data, okay? And your data is from here to here. Extrapolation would be, well, this is where the last piece of information was. What if we wanted to know something out here? What would be the information over here? Well, that would be later on. That we don't have that. That's extrapolation. But if we had to guess, we would follow the line. That point would be higher, somewhere up there. That would be extrapolation. Okay, so the problem that I was just showing you was, let's say you're going to do information here about flights. So here we have air travel recorded in domestic airline company. How can you use the data to estimate the number of air miles people flew in 2003? So what you would do is you would take these numbers and you'd make them into your table. So you would have to go back to this. You'd have to clear all your data. And actually you want to turn this off too. So we clear it all out. Actually, let me refresh it so it goes away and it's fresh. Okay. Okay, so I kind of had to pause the video so I can set it up faster. So what I did was, because these are kind of weird years to use in a graph, instead of starting at 1975, this is year 0, and then I counted by fives. So 5 years, 10 years, 15 years, 30 years, sorry, 20 years, 25 years, 30 years, 35 years, 45 years. So that's why you see these numbers here. These are the years from 1975. Then I put the miles right here. I had to change the settings so you can see it, but there's a scatter plot, right? Now, the line of regression, the line of fit would be using these numbers down here. So I'm gonna write that down really quickly. Write down y equals, I'm gonna round it, 48.88 for my slope. And my starting point is 1400.51. Okay, so I have the information I need for my line of regression. So I can put this away. All right, now, here's what we're gonna do with it. They're asking us, estimate the number of miles people flew in 2003. Well, there is no 2003, right? What are we using? Interpolate or extrapolate? We're gonna interpolate. Because this is within the data, we wanna know what happened in this year right here. We're gonna use this equation. We're gonna plug in a number to represent 2003. Now, 2003, that would be 25 years, 28 years since 1975. So what we're going to do is simply take the x, we're going to replace x with 28. You'd multiply and you would get your answer, and close this out. And that would be your answer. Whatever you get for y right here, that'd be your answer. So I'll let you guys do that, and I'm going to move on to the last question, example number 5. Okay, example number 5. Copy this down. Causation, cause and effect. As x changes, so when x changes, and that is the reason that the y changes. What does that mean? And all the graphs we're looking at x and y. So cause and effect is looking at, is the reason for the change the changing numbers of x. So for example, if you look at this, as you get more sleep, these people are getting higher test scores. So does that mean the reason people get higher test scores is because they sleep better? So like if you went to bed early and took a test, you're gonna ace it. No, right? There's a lot more to it. Because this is limiting, you could only look at 2 things at a time. It only works if you take control of, they study the same amount, they had classes the same amount, they're the same age, they go to the same school. You would have to take care of all these requirements because the only things you're looking at are these 2. So you can't say this is cause and effect because you're not looking at all the other factors and you didn't control the other factors. So you don't know if this is all from one class. You don't know if this is all the same age group, okay? So this would be no, this is not causation. So causation doesn't mean the same thing as correlation, because there is correlation, but that doesn't mean it's causation, okay? So like here, The temperature increases the number of beachgoers. So as it gets hotter, more people go to the beach. Okay, so maybe, possibly, this could be cause and effect. But again, you'd have to control, is it the weekend? What day are they going at? Is this like in the morning, in the noon, nighttime? You'd have to control for a lot of variables just to make sure that this is true. So I'm not sure about this, possibly, but I'm not going to say it's causation. I think there is a correlation, but temperature is not the only reason people go to the beach. Could be a holiday. Okay, so that's it, guys. That's the last one, causation.